All right, 3.4 polynomial functions. Graphs. Applications. And models. So this is going to be a lot of like what's happening to the graph at a particular point. So the first one say, graph each function, determine the largest open intervals of the domain over which each function is increasing or decreasing. And so we're going to actually use your calculator to graph the function, and then we're going to look at it from there. So the first one is going to be number 10. F of x is equal to 1/4 x to the 6th. So you'll go to y equals, and then type in that function. Is your calculator dead?
Yeah. It actually is dead. It's at home.
Dead at home.
Yeah. What kind of charger does it use?
I don't know. I have a charger in here if you have the kind that charges. If you have one like I have, though, or like Tori has,
It looks like that, kind of.
It doesn't. It doesn't.
It's the exact same as that.
Then it just needs batteries.
Oh, okay.
That one doesn't charge.
How do I?
If it's the flat kind, like the newer ones, then they do.
How do I?
But if you're using one that your brother or sister had, then it's probably like this and probably doesn't charge.
Okay.
But you can tell if you look at the back, it has, if it's thick, it has batteries. If it's thin, it doesn't. All right, so when you plug it in, zoom, so at the top, and then the number 6, which is standard. And then we're looking at what's happening in here to see where it is increasing and decreasing. So we're trying to say, now decreasing is obviously where the graph is going down. Increasing is where it's going up. So we need to figure out at what point it actually turns around and goes the other way to get that. So we're going to hit zoom and then box, which is number 1. Where's the thing? Oh. You're going to arrow down and to the left a little bit till you're somewhere over in this region, because I'm trying to see what is happening in here. I know that the graph is coming down this way, and I know over here it's going up, but I don't know at what point it's changing. So I'm going to try to zoom in on this area here. Then you arrow up, arrow over, and so I'm boxing this little region right here. Okay, it's gonna, I guess. Guess we're going to be playing a little bit of a guessing game because it's not, hold on. Give me 1 second. I'm going to see if it'll, or wait.
Did you graph it at all? So you didn't put that in?
All right, so this one, it's kind of hard to tell, but it looks like this one actually is going to be at 0. So if I go back to where I was boxing it, this one's not. Hopefully a different one that we look at will be a better example of this, because it's kind of hard to see in this one. Because I'm trying to see at what point the graph goes from going down to going back up, and it's obviously somewhere in this region, but there's not enough that we can actually see that. So I would just say somewhere around 0, kind of split the difference based on where that is given this particular situation. So decreasing from negative infinity to negative, or not negative, I guess, to 0, and then increasing from 0 to infinity. This one's not a good example. I think the next one that we do should be a little easier to see. I won't give you one that's like that hard to try to figure out. And just so you know, like, it is possible that it can be just increasing or just decreasing. Like, the function doesn't have to be, like, there doesn't have to be an interval of decrease and increase. If the graph is just going up or just going down, obviously it's not going to have. Let me check this one before I... Okay. 16. This one should be easier to see. F of x is equal to x plus 2 cubed minus 1. So, put this one in the same way. Cubic function will be easier to see. Because there's not as much happening in it. So it should look like that when you type it in. And then hit zoom 6. So what does it look like is happening in this graph? It's going where?
Up. It's increasing.
Yep.
And technically decreasing.
It doesn't actually decrease. Cubic function doesn't technically decrease. Or, well, it can if it's reflected, but anyways. But yeah, it looks like it does here, but it actually just keeps going up the whole time. So this is constantly increasing. Okay, so this one would be increasing only from negative infinity to infinity. Because it's constantly going up.
So where does it start from?
Like, what's the, like, base cubic function?
Yeah, like, if it's...
I'll show you. I'm going to put them both on here so you can see it. So this would be the parent cubic function here. So it starts at like the origin, and that's just the parent function. So this one was shifted left 2 and down 1. This particular one. But that doesn't change anything in terms of our intervals of increase and decrease. The only way that would is if the graph was like had a part where it's going down, because if it's shifted, then we're looking at x values when we're talking about increase and decrease. So like if it was, let's do x squared minus 3 then this one would be, so if we had, I'll just do this, f of x equals x squared minus 3, then it would be decreasing from negative infinity all the way down to here, which is going to be 0. Let's decrease. And then increasing from 0 to infinity, because it just keeps going like that. But if instead, I'm going to modify the problem. If instead I had now, I just changed where the parentheses is, basically, so I now have f of x is equal to, in parentheses, x minus 3 squared. That's what I have. So this one now got shifted to the right 3, so that means that I am decreasing from negative infinity all the way over to 3. And then I'm increasing from 3 to infinity. These ones are a little easier to see than the ones they give in the book. I don't know why they give such weird ones. But does that make more sense? Mm-hmm. So, yeah, so we're looking at x values when we're talking about the interval of increase and decrease. We don't care what's happening with the y. Okay. Next thing. Use an end behavior diagram. So those are basically it's like this, this way, or that way. When it says end behavior diagram, that's what they're talking about. To describe the end behavior of the graph of the polynomial function. Now, all we care about when we're looking at end behavior is the highest powered term. So,
are those little spaces in between?
Yeah, they technically don't have spaces because it's a graph, so it's going to just be one continuous thing, but that's how they draw them in the book. That's why I drew them that way. In the little, like in the instructions, they have those drawn for you. But I wasn't going to try to explain that verbally. It was easier just to write them. So they give us problems. F of x is equal to negative x cubed minus 4x squared plus 2x minus 1. So all I care about is the highest power term. So the only one that I'm even going to look at is this negative x cubed, okay? Because cubed is the biggest thing I have. Now, be careful, it's not always the first term, because if they don't have it written in standard form, like if they have the terms out of order, that won't be the case. But whatever sign is on it as well, so that's why the negative's included with it there. We're going to look at that to determine what we're going for. So the instructions imply that you know what a cubic function looks like, or that you know what a lot of these functions look like. What I'm going to tell you is that these two here, just gonna draw an arrow. These two are odd functions. Okay, so like 1, 3, 5, 7, so on and so forth. These ones over here are even. So if there's an even power, the end result is going to be going the same direction. If it's odd, they're going to be going opposite directions. So one's going to be going to positive infinity, one's going to be going to negative infinity when we're talking about in behavior. If they're even, they're both going to negative or they're both going to positive. So, which situation am I dealing with here?
Odd.
It's an odd one. So we know that they're going to be going opposite directions, okay? Now, if you know anything about cubics, which I just showed you a graph of a cubic function, you'll know that in general it looks like this. But this one was reflected, so it's actually flipped and going like that. And like I said, I don't care about any of the rest of this. All I care about is that negative x cubed. Now, I'm going to show you the easier way if you don't know anything about these graphs and what they look like, other than by plugging them in. And I say it's easier. It will be if you go farther in math than just like this class, or even some things like maybe that we do later on in this class, it'll make it easier. But we do it with limits. So we take the limit as x goes to infinity, and we're also going to do in a minute the limit as x goes to negative infinity of the function. I don't want to write the whole function, so I'm just going to write of f of x. So that just means as x gets really, really big, so the farther x goes across, the like what is happening to the graph. So if I were to plug in, say, like positive 500, okay, to this graph, or to this function. So I would have something like negative and then 500 cubed. What is the sign of that going to be? Is it going to be positive or negative?
Negative.
And I don't care what the number is. It's going to be infinity.
Negative.
So this is going to be negative infinity.
Yep.
Okay, when I plug in something like 500. At negative infinity, though, I'm going to plug in something like negative 500. And I'm being obnoxious about it because obviously it's going to infinity and I want you to see it, but you can plug in any like really big number and it doesn't matter. So it would be negative, and then I'm plugging in negative 500 cubed. What is the sign of this going to be?
Positive infinity.
Positive infinity. So these go opposite directions. So as x gets really, really small, meaning it's going to negative infinity, the graph is going up to positive infinity. So this would be how I knew that the graph looked like this. And then as x goes to positive infinity, so as x gets really, really big, it's going down to negative infinity. Okay? Um... 28. F of x is equal to 7 plus 2x minus 5x squared minus 10x to the fourth. So what is my highest powered term in this function? Yep, negative 10x to the fourth. Now, what is that power? What is 4? Even or odd?
Oh, even.
Alright, so this is an even power, meaning that it's either both going up to positive infinity or they're both going down to negative infinity. Okay? So, I know that I'm looking at, no, this isn't going to look like this, but they're either looking like this or they're looking like this, just visually for you to see it, since where I wrote that's way up here. So, I'm going to look at the limits again. To the limit as x approaches infinity, so as x goes to something like 500, so if I've got negative 10 times 500 raised to the fourth, what sign is going to be on this?
Negative infinity.
Yep, so this one's going to be negative infinity. Now, always check the other one just to make sure, you did everything right. But we know that since it's even, they should be going the same way. So as x goes to negative infinity, got negative 10 times negative 500 raised to the fourth. What's the sign going to be on this one? So what happens anytime you raise something to an even power? What happens to the sign on it?
Negative.
Okay, so this would have become positive, whatever 500 to the fourth is, times negative 10, so it would have also been negative, so negative infinity. So this one is going down to negative infinity for its end behavior. So this one would look like that option going down. All right. Use the intermediate value theorem to show that each polynomial function has a real zero between the numbers given. So, intermediate value theorem said that, you have it in your notes, if f of x is a polynomial function with only real coefficients, and if for real numbers a and b, the values f of a and f of b are opposite in sign, then there exists at least one real zero between a and b. So basically, we're going to be doing synthetic. If we get one is negative and one is positive, then there must be a zero between it. So, 48, and the nice thing is we get to use synthetic for this. So we have f of x is equal to 3x squared minus x minus 4. And it says that there should be a zero between 1 and 2. Or it's asking us to decide if there is or to show that there is or whatever. So I'm going to do synthetic for each of these. Okay, so I'm going to use 1. Now I know it's been, we've had a Christmas break since we did synthetic division. So I might need a little refresher here, but we put the number that's over here in the box. We copy down these the numbers in order. If there's a term missing, remember we still put a 0. So this is going to be 3, negative 1, and negative 4. First step, we bring down the 3. Times 1 is 3. Minus 1 is 2. Times 1 is 2. Minus 4 is negative 2. So that means that f of 1, okay, and I'm writing it that way just because that's how the notes explain it. So f of 1 is negative. So that means when I plug in 1 to this function, I get a negative number out. So if when I do 2, I get a positive, then I will know there's a 0 somewhere between that. So I'm going to do it for 2. Now we use the same original number, so 3, -1, -4. Bring down the 3. Times 2 is 6. Minus 1 is 5. Times 2 is 10. Minus 4 is 6. So 6 is a positive number, so that means f of 2 is positive. So according to the intermediate value theorem, now I do IVT for intermediate value theorem just so I don't have to write out the whole thing. There must be a real 0 between 1 and 2. So since 1 is negative and 1 is positive, and it wouldn't have mattered which one was negative, which one was positive, as long as there's one of each, we know that between those numbers, there has to be a real 0. Let's look at another one. 50. F of x is equal to 2x cubed minus 9x squared plus x plus 20. And they give us the numbers 2 and 2.5. So, start with 2. So then I've got no missing terms. So 2, -9, 1, and 20. Bring down the 2. So 2 times 2 is 4. 4 minus 9 is -5. Times 2 is -10. Plus 1 is -9, times 2 is -18, plus 20 is 2. So that means that f of 2 is positive. Then 2.5 for the other one. Same numbers getting copied down. Bring down the 2. 2 times 2.5 is 5. Minus 9 is -4. Times 2.5, that's going to be -10. Plus 1 is -9. Now it's not going to be a nice even number. -9 times 2.5. 22.5, or -22.5. Plus 20, so that's going to be -2.5. So, it's kind of funny that it ended up being the exact same number. F of 2.5 is negative. So we had a positive, we have a negative. So, by the intermediate value theorem, there must be a real 0 between 2 and 2.5. All right, this last thing is going to deal with the boundedness theorem that you had. And so we have a polynomial function with a degree that's greater than 1. If we divide synthetically, or we're going to divide synthetically, if our value that we're dividing by is greater than 0 and all the numbers in the bottom row, so this would be the bottom row of synthetic, are non-negative, so that means 0 or positive, then f of x has no 0 greater than c. If c is less than 0 and the bottom row alternate sign with 0 considered as positive or negative as needed, then f of x has no 0 less than c. So 58 says to show that the real zeros of each polynomial function satisfy the given condition. So 58 is f of x is equal to 2x to the 5th minus x to the 4th plus 2x cubed minus 2x squared plus 4x minus 4. And it says that there is no real 0 greater than 2. Or wait, greater than 1. Sorry, I'm reading the wrong problem. So that means, based on what our boundedness theorem said, no real 0 greater than 1. So that's part A of our boundedness theorem. That means that the entire bottom row should be non-negative when we're done. So I'm going to plug in 1. No missing terms, so I just copy down the numbers. 2, negative 1, 2, negative 2, 4, negative 4. So I want all non-negative numbers, so that's what I need to be able to prove this. So bring down the 2, times 1 is 2, minus 1 is 1, times 1 is 1, plus 2 is 3, times 1 is 3, minus 2 is 1, times 1 is 1, plus 4 is 5, times 1 is 5, minus 4 is 1. So all these numbers down here are non-negative. So since 1 is greater than 0, and all the numbers in the bottom row are non-negative, there is no real 0. Greater than 1. So this section's a lot of just like proving things. So at least you know what you're trying to get to. All right, one more problem and then we should be wrapping up. 60, f of x is equal to x to the 5th plus 2x cubed minus 2x squared plus 5x plus 5. And it says that there is no real 0 less than negative 1. So in this situation, according to the boundedness theorem, then at the bottom, in that bottom row, what we should see is alternating positive and negative values. So it should be like positive, negative, so on and so forth. Or there can be a 0 in there as well, and a 0 counts as whatever sign we were looking for in that spot. So negative 1. I'm missing the x to the 4th term, so I got to put in a 0. So I've got 1, 0, and then 2, negative 2, 5, and 5. So bring down the 1. 1 times negative 1 is negative 1. Plus 0 is negative 1. Times negative 1 is positive 1. Plus 2 is 3. Times negative 1 is negative 3. Minus 2 is negative 5. Times negative 1 is 5. Plus 5 is 10. Times negative 1 is negative 10. Plus 5 is negative 5. And so across the bottom, I've got positive, negative, positive, negative, positive, negative. And so since negative 1 is less than 0, and the numbers in the bottom row are alternating sign, there is no real 0 less than negative 1. All right, any questions about any of those? Anything at this point? All right, so your problems are going to be 9, 13, 21, 25, 47, 49, 57, and 59. Now, just to give you a rundown, tomorrow, homecoming stuff, we're going to go over at a little after 8:30 so that we can do a walkthrough of what's happening and all of that. I have to be over there to help with that, so I'm going to give y'all the option to either stay in my room and work on these problems, or you can come over with us to the sanctuary and just sit in there and work on them, because that's where I'm going to be.
I wish I had to do something.
Huh?
I have to do something tomorrow.
Yes, you do.
I don't know what I'm doing.
You need to be